So we started the recording for this class, and let's go ahead and see for the theory part for the chapter 2, which is simple harmonic motion. আচ্ছা, এই চ্যাপ্টারটা অ্যাকচুয়ালি মোটামুটি সহজ আছে in terms of content. Simple. The first thing we're going to do is define what we mean by simple harmonic motion. So we're going to talk about a lot of definition, and then we're going to jump into the content. The first definition that we have is, what do we mean by simple harmonic motion? What kind of motion should be defined by simple harmonic motion? The primary defining property for simple harmonic motion is this, where you need to consider both of these quantities as vectors. Simple harmonic motion, an object's motion can be defined as simple harmonic motion if at any instance of this motion the acceleration is directly proportional to the negative displacement. এই কথাটার মানে কি? Let me explain what it means. But before I jump into this thing, there are two more properties of the simple harmonic motion. The other thing is that simple harmonic motion should be linear, and the third property is simple harmonic motion is periodic. It means it should have a repeated motion about the equilibrium. One of the very simple example for simple harmonic motion is simple pendulum. I'm not showing you simple pendulum to begin with, because simple pendulum uses a pretty gross approximation where a certain arc path is to be considered as a straight line path. Other than that, a more understandable version can be this. Let's say we have a wall and we have a smooth surface over here. So this is a fixed wall and a smooth surface right here, and we have a spring, horizontal spring loaded with the wall, with which we have a mass attached over here. You have to understand the friction of this surface is 0 and smooth surface. So, and this is the natural length of the spring. Let's say up to the center of the object, this is our initial length of the spring. Let's say this is our L prime. Sorry, L. Not the entire spring. We are considering the effective length to be up to the center of the object. Now, what we can do, let's say we're going to pull this object by a distance of something, let's say to the right side, and then we're going to let it go. So what's going to happen whenever we're going to pull the object to the right side, then let's say the mass of the object is m. Okay. If we pull it to the right side, the spring is going to undergo some amount of extension, so potential energy would be stored within the spring. And if we now let go, the spring is going to pull the object closer to itself, because it's going to try to retract to its original length. In that process, whenever we have moved this object to the right, we have stored some EPE, elastic potential energy, within the system. So some sort of potential energy was stored. In this case, because it's a spring material, the energy is potential energy. Whenever we're going to let the object go, that potential energy is going to start converting into kinetic energy, but up to a limit. Try to understand. Let's say the object is beginning its journey from this position. So this was my starting position. Let's say this much distance is, I can write it as A, because this will be our amplitude later on. So let's say this is the A amount of movement that we did to begin with. As the object is going to travel from the right towards left because of the pull of the spring, up to this much movement, we're going to have EP converting to K. Up to this much distance, EP will be converted to K. You have to understand, I define this surface to be frictionless, which implies there will be no frictional loss. And because this is a horizontal surface, GP is not involved either. The moment the object reaches up over here is going to have some velocity. So let's say that velocity at this point is written as Vmax. If you wonder, why am I writing as Vmax? Because the subsequent motion is going to be, because of inertia, this mass is going to start going to the left, keep on going to the left. But as the spring will go past this equilibrium position, or the stable position, or something that we call also the rest position, all of these pretty much mean the same thing. It is the position of the object where it has equilibrium of forces. As the object will go back to this position, it is going to start squashing the spring. The spring is going to start become compressed. So naturally, the spring will try to push the object to the right, where the object is actually traveling to the left because of its inertia, because it gained some kinetic inertia as it traveled from the very right side towards the equilibrium. So while it was moving in this direction, the force was also working in this direction, but the value of the force was actually somewhat changing, because you have to understand that force is given by F equals to kx, where x is where x shouldn't be a vector, where x is actually the deformation of the spring. When the object was at the very right position, you had the highest amount of deformation of the spring, so most amount of K EP was stored. Exactly at this position, the EP amount can be written as half kx squared. This expression is coming from the AS discussion. If you remember from chapter elasticity, that stored energy within a elastic body can be given by, within a spring can be given by half kx squared. As the object is going to travel from the right towards left, EP is going to keep on converting to K, and the force which is responsible to do this pull is slowly going to reduce, because at this position you have the biggest amount of deformation of the spring x. As the object slowly travels towards left, so it goes closer, the x is slowly going to become down and F is slowly going to become down. However, up till this position of the object, that pull direction would remain the same. So you're going to have a reduction of value of the force. The spring is going to pull on less strongly, but it's going to keep on pulling in the same direction. That's the important bit. And so this is how the force is going to work out. And also we can write that if is a vector quantity, so we can write that MA equals to KX. Now this is the important part that you have to understand. If we consider x as the displacement of the object starting from the equilibrium, try to understand this thing. Let's say we consider this is our starting position where x equals to 0, and exactly at this position our initial displacement was x equals to capital A. And then if we let the object go, as the object will travel from the very right towards the central position, the x is going to slowly become less. In this case, I'm defining the x as the vector quantity of displacement of the object. Let's say here I define it as the deformation of the spring, which is also okay. X is also used for the deformation variable. But if I now want to use that x expression as displacement, in that case you have to understand that this is our starting position towards right, considering to be positive. When the object is on the right side of the equilibrium, x should be positive as a vector. But for that duration, force is working to the left, which means if you consider the direction of the acceleration, it's working on the opposite direction. So if I want to equate these two forces, I must write minus MA equals to KX. Or in other terms, I could have written that the resultant force on the object should be opposite direction compared to the elastic force of the spring. So I should not write this equation. Can you লিখতেছেন সেটা একটু পরে বলতেছি, don't worry. So when the object is on the right side of the equilibrium, acceleration is working towards negative directions because it's working to the left. So this is actually where the minus sign is coming from. So if I subject the acceleration vector from here, I can write a minus k by m, which is basically gonna work as our constant. So this much is our constant multiplied by the displacement vector. This is gonna happen for the right side. When the object is going to start traveling from the equilibrium towards further left, the maximum it can go on the left side is also by a distance of a, where in terms of displacement I might write that is equals to x equals to minus a. This is the maximum displacement it can go to on the left side. Within this process, the spring is going to become compressed. Now the moment the spring becomes compressed, it will start to push the object towards right, because spring becoming compressed means it's going to try to retract its original shape, it's going to try to expand. So for this entire journey, the acceleration is going to work this way. So the moment from the moment the displacement starts to become negative, the acceleration immediately becomes positive. Try to understand. For this whole journey, x was having a positive value. It was slowly becoming less and less and less. Acceleration was also becoming less and less and less. But they were working in opposite direction. When x is positive, acceleration working towards the left direction because the spring is pulling it. When the object moves past the equilibrium position, the spring becomes compressed and the spring starts to push the object to the right. But whenever the object is on the left side of the equilibrium, the displacement becomes negative. So when the displacement is becoming negative, acceleration is becoming positive. So the direction of working for these two vector variables, one is the acceleration on the object, the other one is displacement of the object from the equilibrium. These two things are always going to work against opposite direction of each other. This is basically the defining equation of a simple harmonic motion. And as the object is going to travel from this point to this point, if we want to go for the conversion for energy, here it has the maximum kinetic energy because the velocity was maximum. And as it slowly travels from here to here, it is going to slowly slow down. And right whenever it reaches at this position, let's say I'm drawing it to the blue dotted rectangle. At this position, all of that kinetic energy, which was over here, will be converted to potential energy, elastic potential energy of the spring. So the object is going to slow down and eventually ultimately reach a speed of v equals to 0 over here. So if I want to show all of the variables for multiple different stuffs over here, have a look at how it works. I'm going to use this part of the screen over here, board over here, to give a better understanding. When x equals to 0, at this value, we're going to have v equals to v max. At this position, you have instantaneous velocity 0. At this position also, you have instantaneous velocity 0. When x equals to plus a, I might as well write plus, just to represent it's the maximum positive displacement. At this position, acceleration is going to be minus acceleration max. Now you have to understand, acceleration max in this case represents the maximum value of acceleration that is working at this position of the object, whereas the minus sign is representing that it's going to work in the towards the negative direction. When the object is at this position, then the acceleration is going to be plus acceleration max, because when the spring is squashed, the object is going to start experiencing force to the right. And exactly at here, when the spring is at its perfect original length, by the formula of elasticity F equals to kx, if deformation is 0, you're going to have 0 force as well, which is going to give you F equals to 0, which ultimately tells you that at the equilibrium position, acceleration will be 0, which means when x equals to 0, a is 0. As x is increasing, a is also increasing. At maximum a position, maximum displacement position, you have maximum acceleration, and at maximum displacement position, you also have maximum acceleration. The only key part is whenever x is positive, for all of those places, acceleration is negative, and vice versa. Whenever acceleration displacement is negative, for all of those positions, acceleration is positive. So this is how the whole oscillation motion works. I have not gone over to the part for what happens for the other motion. So what I've been telling you, I'm going to use maybe a different arrow, maybe I'm going to use black. I started my observation from here. So from here to here, the object speeds up. From here to here, the object slows down to 0. Then again, from here to here, the object will once again speed up, because for this part, the acceleration working to the right and displacement is negative. So you have to understand, for this part, speed is going down. The object is, sorry, speed is going up, my bad. For this much duration, whenever the object is traveling towards the equilibrium, the velocity is going up. The moment the object is traveling away from the equilibrium, the velocity is going down. Then for the next part, when the object is once again traveling from the left extreme position towards the equilibrium, the speed will once again start to go up. And when it will travel from the equilibrium towards the other terminal position, the speed will once again go down. So important observation, motion towards the equilibrium always causes the speed to go up, because for these motions, if I write over here that motion towards equilibrium need more space. Maybe I'll keep it right here. Yes, motion towards equilibrium gives you speed up, which basically means that we're gonna have some sort of potential energy will be converting to kinetic energy. Now I'm using the word some sort of potential energy because in this case I'm using using a spring loaded mechanism in which for which it is now the elastic potential energy. For other oscillation cases, we can have electrostatic potential energy. We can we can have the gravitational potential energy for a simple pendulum, or maybe for a vertical spring. So you will have some sort of potential energy that will be converted to kinetic energy of the object. And whenever motion away from the equilibrium, so if it is motion towards the extreme position, or that's why I'm writing motion away from equilibrium, that would be slow down, which would lead to kinetic energy of the object slowly gets converting to potential energy. So this is how the very basic idea of oscillation works. Here we have already seen that we could actually get to the equation A equals to minus Km. Actually, I should have written the bracket inside. Shouldn't have written the bracket. So A is proportional to minus K by m. So this is actually a constant. K is the spring constant, m is the mass of the object which is undergoing oscillation. So ultimately you should get A proportional to minus x from this expression. Even if this is a different scenario, we can still get this expression from all the cases of simple harmonic motion. If the motion of an object can be ultimately derived or expressed within this proportionality, that vector acceleration is directly proportional to negative of vector displacement, then that motion will be defined as simple harmonic motion. That's the definition, and also a simple example, maybe not so simple, because I included a lot of different variables over here. This was a total discussion for what happens for a single horizontal spring loaded object for the simple harmonic motion. A drawing and discussion to go buঝা গেছে কিনা. If you have any question, I'll take questions now. I'll put the whole thing in view, more or less. Anyone? Question?
না স্যার, ঠিক আছে।
No else? Zarif, Tausif, Uzma, Ifat? Acha. Okay, so the next thing that we have to consider, the simple harmonic motion by virtue should be linear, because you do understand that if A is proportional to minus x, this have to be perfectly in opposite direction. So nonlinear motion cannot be simple harmonic motion. This second bullet also has a little bit of, what can I say, Shubhankarer Faki. Shubhankarer Faki mane hocche, sometimes for convenience's sake, we can do a gross approximation of this whole logic. I'm going to show you this for the simple pendulum scenario. And also simple harmonic motion will be periodic, which means the same position of the motion will be repeated every once in a while, which we call the periodic motion. Now, if we observe, so that's how we define the simple harmonic motion. The other definitions that you need to remember, or you actually know this stuff, so I'm gonna try to brush up your memories a little bit. We have to understand what do we mean by time period, which is given by capital T. We have to understand what do we mean by frequency, which is given by F. We also have to remember the term, to some extent we have to understand the term phase. What do we mean by the word phase? No,
the complete oscillation.
Time period is basically the time required for one complete oscillation. Beautiful. So whenever the oscillating object reaches to the same position of its reaches to the same position from the same direction. These two variables are important. That's why how we define one full oscillation. The amount it takes for one full oscillation is time period. How many full oscillations are covered within unit time? Don't write 1 second in definition. Write unit time. How many full oscillation complete oscillations are made within unit time is defined as frequency. And phase is actually not a measurable quantity, although sometimes the phase angle is measured in degrees. I'll tell you what the phase of a certain oscillating particle is. Before I do that, let me just show you the definition from YouTube, maybe. Sorry, from আচ্ছা ঠিক আছে, তাহলে এটা আমি আপডেট করে নিব, ডোন্ট ওয়ারি। কি যেন লিখতেছিলাম, definition of phase. Let's have a look at it. And then I'll tell you what you should understand. Phase of oscillating particle at any instant is a physical quantity which completely expresses the position and direction of motion of particle at that instant with respect to its mean position. So phase of an oscillating particle at any instant is a physical quantity which completely expresses the position and direction of motion of particle at that instant with respect to its mean position. So basically here, the phase of a particle is actually defined as a certain quantity that handles with the position vector of the oscillating particle with respect to the mean position. Position vector. If you guys understand, try to understand what is position vector. Position vector is basically the displacement vector of a certain object with respect to the equilibrium, or with respect to the origin. You can also use the origin in some cases. That's how what we say position vector. So how far it is and in which direction it is, together these two quantities make up the position vector. So phase actually can be used in a lot of cases. So phase is a quantity that tells us where the particle is located within its motion. We're going to see how this phase property, or which will be expressed by some angles for the upcoming part of discussion, more detailed for in the next part. Do we have the vertical spring right after that? We don't. No, we don't. We have this conversion over here. Okay. Whenever scientists were actually handling with the oscillating force stuffs, what they came to find across that the motion of an oscillating particle, the linear motion of an oscillating particle, can be expressed by the projection of a uniform circular motion object. I'll say this again. Scientists came to find out that the motion of an oscillating particle can be perfectly expressed, or which is homologous, or homologous in this case would mean that it was similar with the projection of an uniform circular motion. Now, what do I mean by the projection here? This word projection might mean shadow. This might mean the view from side. This might mean the side view. One of the physical setup, which is actually very well given in your worksheets. I can actually show you this setup, which might make some good sense and help me write a bit less. Is this scenario? Have a look at this scenario. A vertical peg. A vertical peg is attached to the edge of a horizontal disc of radius r, as shown in figure 4.1. So there is a peg over here, just a wooden stick attached with one of the sides. This is a disc with a radius r. The disc rotates at constant angular speed omega. A horizontal beam of parallel light produces a shadow of the peg on a screen, as shown in figure 4.2. So try to understand what is happening. We have made this vertical with this. We have made this disc to rotate in a vertical plane. So we have maybe attached a rotor at the center, which is behind this thing, and the peg is extruding out of the screen, and it is rotating at an uniform speed. So the omega is the constant, so its angular speed is uniform. We have sent a parallel beam of light over here. It's very important it is parallel, otherwise we are not going to have congruent variables over here. And as the parallel beam of light is going to keep on going over here, we'll definitely have the entire diameter of the whole disk on the screen. But along with that, we should also see that this peg is going to produce a vertical shadow over here, a horizontal shadow over here, because now this peg is actually horizontal, which is vertical with the face of the disk, so the shadow of the peg should be horizontal in length. And as the peg is going to keep, as this whole disk is going to keep on rotating, this shadow, which is a two-dimensional expression of this three-dimensional movement, is going to keep on go up and down on the screen. So there are actually good animations of these stuffs as well. Exactly. So this is from visual physics. I'm gonna show you this video. Might as well get a copyright French stuff. If so happens, so this part of the video would be deducted from the actual lecture, but you do see I just wrote SHM animation by shadow. This is the second video that shows up in the Google search, so you can also look at that up at any time.
Very interesting point about a simple harmonic motion is that It can be considered as a projection of a uniform circular motion.
So this is the beauty of it. Have a look. What this person is doing, he's
With that,
showing you this
it can
motion
be considered
in a line, and it is appearing to be a vertical motion. But now he has a background of a 4 walls maybe, and he's going to start to rotate this whole setup, and he's going to show you that this object was actually going around in circles. So that's the beauty
as a
of it.
projection
So that's why the background would change. Have a look.
of a
When
uniform
the
circular
background is
motion.
rotating, so this whole thing, this whole motion is now appearing to become circle.
That is, a uniform circular motion, when viewed sideways, is a simple harmonic motion.
So uniform circular motion when looked sideways is
We
uniform.
can also consider a simple harmonic motion to be a shadow of a uniform circular motion.
There it is. Or this is how the projection works. This is actually animation.
Let us say that the angular speed of a particle moving along a circular path
এই আইডিয়াটা বোঝা গেছে কিনা about the shadow, that circular motion horizontal projection বা two dimensional projection is expressed as simple harmonic motion. Why this is simple harmonic motion সেটা একটু পরে তোমাদেরকে আমি প্রুফ করে দেখাবো. It will be very visible, very much visible from the drawing and all the calculation. But do you understand the concept that I'm trying to give you? এটা কি বোঝা গেছে কিনা?
Yes, sir.
The whole thing about the side view or horizontal projection. It doesn't have to be horizontal projection, it can be also vertical projection. You could, if we shed some light from the top and use the horizontal screen over here, we would see the shadow move left and right. That can be also simple harmonic motion. Basically the side view of a uniform circular motion, or you can say the shadow projected of an object which is undergoing uniform circular motion from the side with the parallel beam. So how does this whole thing work? Let's have a look at the whiteboard, and I'm going to start give you some properties. So I'm going to choose a bit smaller thickness for the circle, make it a circle. Beautiful. Okay, so let's consider this is the path of a certain circular motion object, bit above, bit left. Yes, here is the center of the object, center of the circle, and here is the object right over here at this position to begin with. So here it is at t equals to 0, and we're going to observe the motion of this circular motion along this line. So this line is going to give us the two-dimensional view or the shadow. So we're going to send parallel light from here, and maybe the peg is at the center, or maybe circular object is over here, so it's going to go up and down, and the shadow is going to be observed as the simple harmonic motion, where the circular motion is happening within the circle. At this position, the object has 0 displacement at t equals to 0. So we are starting our observation from here. The object is going to keep on rotating in circular orbit, no big deal, and the position of this shadow is going to go up. So the maximum this object could rise in the vertical axis is over here. So when the object is going to come over here, let's say with a speed with this motion, then the shadow is going to fall, or the projection is going to fall right over here. And this is the place, or the maximum distance, what we define as, let's say x equals to plus a. When this is going to happen, I can write that if the total time period of the whole motion is considered to be capital T, this is going to happen at 1/4 time of t. If you wonder why 1/4, because try to understand, if the object starts from here, it will take capital T amount of time, or time period amount of time, to reach up all the way over here. So if I just divide the whole circle into 4 parts, have a look, 4 parts. So one arc, 1/4 of a circle, second arc, another quarter of a circle, another quarter of a circle, another quarter of a circle. So all of the quarter end positions are going to take t/4 amount of time. So the maximum distance can be plus a. In this case, obviously I'm considering the arc to have a radius of a. The circle has to have a radius of a. And the lowest position can be somewhere over here, which if I if I project on the screen, this is going to be somewhere over here. This is going to be x equals to minus a. And because I started from here in an anti-clockwise circle, the amount of time it's going to recur is going to be twice the time period. And eventually at this point, it can reach up over here once again. So this is going to be also available at full time period time. So I'm going to be writing 0, t, which means the object will be seen, this shadow is going to be seen over here at 0 time. And this shadow will reappear at this position, completing one full cycle at t equals to t as well. However, interesting enough, while it was going from here to here, when the particle is gonna cover this half circle, is the shadow will also reappear here as well. So it might be also a good idea if I just write all the time frames so that we can keep track of it later on. So I'm writing 0, t by 2, t, because when it is rising up, it takes t by 4 to reach over here. It takes another t by 4 to drop down here, which is t by 2. It takes another t by 4 to reach all the way at bottom right over here, which is 3t by 4. And then in another t by 4 amount of time, quarter of time period time, it reaches up to the equilibrium position once again. So that's completing a full circle or taking a total amount of t or time period amount of time. To derive the equation, what we're going to do, let's assume that we're going to consider any random position on the arc. Let's say the particle started its motion from here with uniform circular motion. Let's say the angular velocity is omega. We know what angular velocity is from the earlier chapter. And let's say within a time amount of t, the particle reaches over here. So this is a random position on the arc. The shadow or the position of this position is, let's say, falling over here. So this is the position we are now defining as our variable x, which we are going to try to express with some mathematical expression. And let's say the amount of time it takes to reach over here is given by small t. So our current job at this moment is to find out how much is this. We're going to try to express this displacement in terms of in small t. Now here's the deal. The angle that it produces with the horizontal, let me use a different color. The angle that it produces with the horizontal or with the initial position is, let's say, theta. And we can write, and if I draw a vertical from here over here, I can say that this side is gonna be a sine theta. Can everybody see this? Or does this triangle make sense? I'm just trying to find out what is the vertical displacement over here. That's why I drew this thing, because this red line and this projection length over here are going to be exactly same. ঠিক না? So এখানে আমি যে জিনিস লিখতে পারবো সেটা হচ্ছে ultimately here this displacement x can be rewritten as x equals to a sine theta, or theta can be also replaced by a sine omega t, because theta is given by angular speed into time. Theta equals to omega t. So that's the expression for our displacement vector. Now, interesting enough, if we start to differentiate this equation to get the other variables, we're going to come up with the velocity and the acceleration as well. So let's, other than scribing on this figure any further, let's try to do that. What we have found out, that the displacement vector is given by a sine omega t. তোমরা সবাই differentiation তো পড়ছো না?
জি স্যার।
I believe so. So আমি যদি velocity vector বের করতে চাই, simply আমাকে কি করতে হবে, এই এক্সপ্রেশনটাকে ডিফারেন্সিয়েট করতে হবে. So I'm going to have to do dx by dt. This is going to give me omega a cos omega t. Sin becomes cos and the omega comes as the multiple of the whole expression. If I want to get the acceleration out of this expression, this is going to be dv by dt, or this is basically the double derivative or second derivative of the x dt squared, which is going to be, this is, I'm going to now try to differentiate this. Cos ke differentiate korle hobe minus sin. So minus টাকে আগে লিখলাম, sin omega t কে এখানে লিখে ফেললাম, আর আগে একটা ওমেগা ছিল, এখন আরেকটা ওমেগা আসবে, দুটো ওমেগা মিলে হবে হচ্ছে মাইনাস ওমেগা স্কয়ার, আর এটা কনস্ট্যান্ট হিসেবে সামনে বসে পড়বে. So ultimately this is coming that a equals to minus omega square a sine omega t. And you can see that this sine omega t earlier was expressed as x, which means I can replace this thing over here. I'm gonna get a equals to minus omega square x. If I take this part as the constant out, I can still get that proportionality that we talked about in the beginning, a proportional to minus x, acceleration proportional to the negative displacement right over here with a very beautiful expression, thus proving that this motion of this shadow, not the whole circular motion, the projection is going to maintain a perfectly simple harmonic motion, because we can ultimately get acceleration is directly proportional to the negative displacement. So that's basically how the equation set works. I'm going to zoom out a little bit so you can see the full thing in a single snap. Take out this calculation value, all the written numbers over here, and see if you have any question. আচ্ছা, এটা ছাড়া আচ্ছা আমি এটার পর আরো দুটো অ্যাডিশনাল জিনিস বলতেছি। I'm going to write with green, সেটা হচ্ছে this set of equations were obtained under one specific starting condition, সেটা হচ্ছে we defined when t equals to 0 x was also 0. Take a very good look. If you wonder এর থেকে ডিফারেন্ট কিছু কি হওয়া পসিবল, অবশ্যই হওয়া পসিবল, সেটাই আলাপ করতেছি। We started to observe the motion of the shadow. We started to observe the motion of the simple harmonic motion shadow when the particle was starting from its equilibrium position. It means this object is continuously rotating by, the shadow is moving up and down. We started our observation deliberately when the shadow was crossing the equilibrium position. That's why at t equals to 0, our initial displacement was also 0. So our initial position was from the equilibrium. That gave us these three set of equation: x equals to a sin omega t, b equals to a cos omega t, and we also got a equals to minus omega square a sin omega t, which ultimately led up to the proportionality. One of the important different position that we consider in your syllabus is, what if we want to observe the motion of the particle from one of the terminal positions? So let's say if it so happened, so I'm going to write this with green, I'm going to extend this line and give a mark over here. So if it so happens that if we want to observe the motion of the particle starting from here, let's say when x equals to plus a, then t equals to 0. If that happens, t equals to 0. So if we want to start the observation from this point, what's going to happen? Well, you can see that this is a positive a angle. So in this case, simply this whole expression changes to x equals to a cos omega t. Now you might wonder, where does this whole cos omega t thing comes from? I could show you where does this cos omega t actually comes from. I could actually make this move around from here to here, where this angle is going to be theta. So the actual angle it move from here to here is going to be 90 minus theta. So ultimately the sin expression reverts into cosine information. I'm not showing you the derivation, but if you're interested, you can look it up in Google, or I can show you the derivation. The derivation for this part is not important for your syllabus. What is important, that if the observation of the particle is started from one of the terminal positions, if the particle was considered to begin its journey from one of the end positions, from one of the extreme positions of the oscillation, either from plus a or minus a, then the ratio that we're going to be using is going to be cosine ratio. If you start observing from here, you're going to get a cos omega t. If you start your observation from here, you might as well get minus a cos omega t. That's also possible from the negative displacement. That's also possible. Even whenever we have this expression, this whole set of formula can be still obtained. Have a look. X equals to a cos omega t. So velocity is going to be the first derivative of this one, which is going to be minus omega a sin omega t. And the acceleration is going to be once again minus omega square a cos omega t. Take a look at this differentiation. First derivative, second derivative, which ultimately gives you a equals to minus omega square x, or leads up to a is proportional to minus x. So additional information that we just learned is that if we start our observation from one of the terminal positions, we should use the expression x equals to a cos omega t. But if we choose to start from the equilibrium position, it's going to be a sin omega t. This choice is going to help you solve a lot of mathematical problem, much too easily, so that you wouldn't feel confused and you can actually use it pretty well. For those of you who might feel like this is a monorack book, we might, there's a likelihood we might forget this. Well, here's the deal. You are not going to forget this because of this thing. Just remember that there are two different trigonometric ratios involved, sine and cos. Whenever x equals to 0, our equation was x equals to a sine omega t. So if you place t equals to 0 over here, you get sine 0. Sine 0 gives you 0, a into 0 gives you 0. So in this expression, a sine omega t, placing t equals to 0 by default brings up x equals to 0. But if you want to get x equals to maximum value, that can be available from here. If you place t equals to 0 over here, think in your head. If you place t equals to 0 over here, you get cos 0. What is the value of cos 0? 1. So you can get 1 from here, and that should give you a. Or if you to consider this position also, if you want to consider that at t equals to 0, the object starts from here, then the equation can be minus a cos omega t. So in that case, you can also get minus a. For those of you who are wondering that why are we bothering with minus a? A is the amplitude of the motion. Is minus a certain thing? I mean, amplitude is supposed to be the maximum distance it travels from one direction. Well, here is the deal. We have defined the x to be a vector. A in this case is a measure of length. Now try to understand. Here is your equilibrium. Let's say here is your equilibrium. Anywhere above this level, x is positive. Anywhere below this level, x is negative. A in this case is actually a measure for what is the amplitude of the motion. So that's why we use the term A. That comes in meters. So if the object is right over here, you might as well say it is at, let's say, half meter displacement, positive displacement. If the object comes up over here, you might as well say the object is at minus half meter displacement. Mentioning minus half meter displacement automatically means it is on the negative side of the displacement axis. So this a is not expressed as a negative quantity. You have to understand that this x, this minus sign, is a property of this thing. This a is basically a number representing where that object is located, how far away from the equilibrium the object is located, how far away, yeah, that's a good expression, is located. But where is it located? Is it located on the plus side or is it located on the minus side? That's basically what this minus or this visible invisible plus sign actually dictates. So position is pretty important, which is defined by the plus or minus sign, and the magnitude of the position is defined by a fraction of the maximum displacement, which is acceleration at a certain fraction, for example, cos omega t fraction, or in some other cases sin omega t fraction. These are the fractions that we use to express where it is. এই পর্যন্ত বুঝা গেছে কিনা? Any questions so far? Maybe not. One additional thing which I'm going to discuss to you right now, which is not perfectly discussed in your syllabus, but still I want to give you a bit of an idea. What if we want to observe the motion of this particle starting from any random position? Let's say I want to start this observation when the particle was right here. So I want to define my t equals to 0 over here. So how am I gonna handle that? There are two different ways. Let's say at this position, when you are considering t equals to 0, the angle it made with the equilibrium line, with the equilibrium position, it makes an angle of, let's say, alpha. Let's say this red angle is alpha, which means this is now alpha angle away from the 0 degree. So in this case, the displacement can be expressed as a sine omega t plus alpha. This actually means that it is expressed as a sine ratio. Expressing a sine ratio means we are supposed to start our observation from this point, from the equilibrium. But since we are starting at alpha degree positive side away from here, we are writing the angle expression as omega t plus alpha. So this alpha is going to be used as a constant or for the phase angle expression. So for all of these parts, if you consider for all of these possible derivations, then alpha will not make any effect because alpha is not a variable that depends upon t. Omega t is that quantity is a t variable. Alpha is just a constant. So if you just derivative, find out derivative of a constant, you basically get 0. So this will not affect your expression of the angle in the equation, substitution equation, but this is how we can express the position of a random the equation of a random position to begin with. Well, if you wonder what if an object starts from here, well, it's possible that maybe this angle over here with the horizontal is minus beta. I'm using minus because it's a clockwise angle. So, and if you want to start the observation from here, if t equals to 0 considered here, you might as well write x equals to a sine omega t minus beta, and then you can just go ahead with your equation. So that's also possible that we can have a little bit of something added with the omega t, a little bit of something separated with the omega t. This will show that we have not started the observation of the particle, not from the equilibrium exactly, not from the terminal position exactly, somewhere in between. And where did we start? That additional plus or minus angle with the omega t defines where was the starting position. এই পার্টটুকু, এই রেড লেখা পার্টটুকু তোমাদের মনে না রাখলেও চলবে, এটা তোমাদের সিলেবাসে নাই. I just prefer to teach this in every batch because I feel like that the CA people, they could at any point come up with an expression like that, and students, if they are not acquainted with this expression, they might lose their cool that what is this additional thing within the angle part came by, what does that even mean? This is what it means. বুঝে গেছে?
Yes, sir.
আচ্ছা, এরপরে আমাদের গাদাখানে গ্রাফ আছে, গ্রাফগুলোকে আমার নোটে আছে, নাকি আমি নেট থেকে বাই করে দেখাবো? ওকে, নেট থেকে দেখালেও হয়. Steps to the right, SHM, time graphs, images. Well, choosing any of this is good, I think. What is the size of this image? Open image in new tab. Yes. Small. Small. Too small. Okay, how about we go this tools size large. What stars? লার্জ দেওয়ার পর এখন আর এক্সেস লেভেল গুলো আসতেছে না, আসতেছে হাইজেবি আসতেছে, বাট এক্সেস লেভেল গুলো আসতেছে না. আচ্ছা, এক্সেস লেভেল গুলো ছাড়াই তোমাদেরকে দেখাই, আমি আমার ড্রয়িং থেকে দেখাই, নো ওয়ারিজ. I'm going to zoom in and I want everyone to attempt to see what is on the axis. Can you see this axis? What is this axis? This is a displacement versus time graph, x versus t. The second one on the same grid sample is velocity versus t. The third one is acceleration versus t. So we have three variables drawn with the same time instances. This graph was drawn for x equals to a sine omega t. So this is the very initial equation, x equals to a sine omega t. So maximum value of x can be plus or minus a. So that's why the peak level is given as plus a. The lowest level in this case mean the maximum negative level, not the zero level. Maximum negative level is minus a. So maximum value of a is plus or minus a. These are shown as the limits on the vertical axis, and this is a sine curve. Velocity is omega a cos omega t. Maximum value of velocity can be plus or minus 1 for the cos omega t value. So Vmax can be plus or minus omega a. That's why it is the axes are labeled as plus omega a and minus omega a over here. These are the two maximum values on two sides of the equilibrium. So you can see this is the scenario like that. It's a cos curve. And acceleration is going to be minus omega square a sine omega t. So maximum value of acceleration can be plus or minus omega square a. So this is a negative sine graph with the same type of time period, and the terminal values are plus omega square a, which is the maximum positive value, and minus omega square, which is the maximum negative value. So these are the terminal values through which these variables can move. This is the set of graph that we have for x equals to a sine omega t. But if we have x equals to a cos omega t, simply this whole graph is going to have a 90-degree shift to the left. So I really did not want to draw this graph, but I can actually take one of these graphs from here. Little high definition would just work. Nice. This is a cos curve. Should I choose this one? No. Should I choose this one? Nah. This is good. Is it good enough? Yeah, this is the cos curve. Might as well use that. So I'm going to paste it over here. Oopsie daisies. Bad idea. দাঁড়াও ইমেজ সাইজ করতেছি। Let's paint it. Paint it নিলো কেন ব্ল্যাক হচ্ছে? Open image in new tab. And then I can zoom in.
Sir,
জি বাবা,
sir, I am a little confused about one thing.
বলো বলো।
কখন sin theta হবে আর কখন cos theta, মানে cos omega t আর কখন sin, এটা একটু confused.
Sure, I'll help. Beautiful. Condition যদি এটা হয়, starting condition, that when you start the observation, the particle is located at the equilibrium. তখন হবে sin omega t. বুঝছো?
জি স্যার।
মানে the particle is moving up and down motion, no big deal, but you are you're choosing to count your time when the particle is crossing through the equilibrium. So at t equals to 0, for your observation, if x equals to 0, then you're going to handle with x equals to sin omega t, a sin omega t. However, if your starting condition is this, or maybe right over here, which I didn't write, x equals to 0 and t equals to 0, x equals to minus a, or maybe this. If your starting conditions are any of these two, either the particle is seen or the object is seen at the positive extreme or maybe at the negative extreme. In that case, your equation is going to be in the cos omega t expression. If on the positive side, you're going to have a cos omega t, which is positive, or if you are on the negative side, you might as well express it at minus a cos omega t.
Okay, sir, বুঝতে পেরেছি।
The cosine sign is defined by your choice of starting condition. Where did you begin? ঠিক আছে? আচ্ছা, এখানে আমরা একটা গ্রাফ পাইছি, ভালো একটা গ্রাফ পাইছি, হাই ডেফিনিশন গ্রাফ পাওয়া গেছে। I'm trying to find out another graph which is gonna be the sine graph. Give me a sine graph. This is a good graph. Yeah, this is actually informative one. Yep, I can take this one. Open image, new tab, screenshot this, copy and paste. So এটা আমি এখানে রাখলাম, নতুন জিনিসটাকে আমি কপি হয় নাই। So I have drawn two different graphs from two different places to show you two different stuffs over here. Although they have numerical values over here, for the time in this are the numerical values. This is the set of graph for x equals to a sin omega t. How can I tell? Because I can say that the first distribution graph is a sine curve. This is the set of graph for x equals to a cos omega t. And practically speaking, these are the same graphs. If you just shift all of these graphs by 90 degrees to the left, what I'm trying to say is that if you just observe your axis, other than here, if you draw your axis through this line, you're going to end up with this graph. Do you see it? মনে করো এইটুক নাই, এই ফিগারের এই লেফট পার্ট টুক নাই, তাহলে আমাদের এটা কস কার্ভ হয়ে গেল না? এটা হয়ে গেল মাইনাস সাইন কার্ভ, এটা হয়ে গেল মাইনাস কস কার্ভ. So that can be also considered to be three different way of expression, but the idea is very same. You can see here we have all the time periods labeled, and here you can also have the time periods labeled. This is quarter of a time period, quarter of a time period, quarter of a time period, quarter of a time period. This is one full time period, and that follows through the whole scenario. In some cases, or in some random or exclusive cases, if it so ever happens that the examiners want you to judge for any random position, not beginning from the any of the terminal position or the equilibrium position exactly, they might actually bug you. They might choose to bug you, which I'm not saying that they should, but they might, with a graph that has some sort of an arbitrary starting point. For example, maybe a graph that looks like this. You can see that this graph is neither a perfect cos curve, neither a perfect sine curve, so it is a bit missing. So this would have something added or subtracted with the omega t part to make this equation, because at t equals to 0, the particle was not starting its observation at any other point. One of the very important thing that is really you shouldn't mess up is the observation of the y-axis variable whenever you are trying to answer any of these questions. What do I mean by that? মনে করো পরীক্ষা তোমাকে একটা সুন্দর সাইন কার্ভ কস কার্ভ দেওয়া আছে, you can see, look at the graph, have a look at the shape, and you are confident that this is a cos curve. এখন তুমি y-axis এর কোয়ান্টিটি কি দেওয়া আছে দেখো নাই। মনে করো তোমাকে একটা গ্রাফ দেওয়া আছে, let's say that one graph is given in a question that looks like this, ঠিক আছে, and here it is saying v versus t, and they are asking you what is the defining equation of this simple harmonic motion particle. The option choices A, B, C, and D, they are all given in terms of x. So x equals to something, x equals to something, x equals to something, x equals to something. So x equals to a sin omega t minus a sin omega t, a cos omega t minus a cos omega t. They have given you all the four options. So let's say a sin omega t minus a sin omega t, a cos omega t, and minus a cos omega t. Now my question is that omega t, for these four options, which one is the correct response? Which one do you think can be the correct response?
D হইতে পারে।
Now that is the most common mistake, which I hope you didn't do, but you did, but that's good. Have a look. What is this variable? What is this variable?
B
Velocity. Is this displacement? No. What are these variables? What are each of these variables? These are all displacement, which means you are provided a VT graph. You're asked to give the answer in terms of X graphs. I'm showing you for an MCQ question. You don't have MCQ in your A2 classes, but this is a good point of understanding. You have to understand that if V has this equation, so this would essentially mean V equals to minus A sin omega t. ঠিক আছে? তো এখান থেকে আমাদের A এর এক্সপ্রেশনটা কি হবে? মানে x এক্সপ্রেশনটা কি হবে? and you তোমার একটা জিনিস খুব কমন বুঝছো যে x এক্সপ্রেশন বাই করতে হলে এটাকে কি করতে হবে? ইন্টিগ্রেট করতে হবে না?
জি স্যার।
and integrate করলে একটা ঝামেলা আছে কি, whenever you're going to do integration, you're going to have another constant. So my preferable way, or the way I personally like, is that don't bother for integration, just differentiate this whole thing, because whenever you're going to differentiate the velocity equation, you're going to ultimately get the x expression within your equation. So if I'm going to differentiate this thing, so acceleration is going to look like what? Minus a, I should have written the omega squared in the beginning, so I'm going to write the omega squared. So minus omega squared, I should have an omega over here. Well, Acha, forget about this omega or omega stuff, whatever. Forget about this. V is a minus sine theta curve, sine t graph. So acceleration is gonna be with what graph? What graph should acceleration be? I'm not writing equation. I'm just writing the basic graph expression. Velocity is expressed as a minus sine t is the variable here. So acceleration এর গ্রাফটা কি কোন ভ্যারিয়েবল দিয়ে এক্সপ্রেস হবে? এটাকে ডিফারেন্সিয়েট করলে আসবে। সাইন কে ডিফারেন্স করলে কি হয়?
মাইনাস কস টি।
মানে পুরোটা এক্সপ্রেশন হবে হচ্ছে মাইনাস কস টি, ঠিক না? এটা কি বুঝতেছো বলবান? I just differentiated it but not showing you. The simplest way to judge. তার মানে অ্যাক্সেলারেশনের গ্রাফ যদি মাইনাস কস টি হয়, আলটিমেটলি আমার ডিসপ্লেসমেন্টের গ্রাফ হবে হচ্ছে কি শুধু কস টি। কেন? কারণ acceleration proportional to minus x. Remember, have a look at all of this expression that we have attempted. এই দেখো, a proportional to minus x. So whenever you had x equals to a sin omega t, you found out a equals to minus omega square a sin omega t. So this minus was actually a part of your proportionality equation. So the whatever you had remaining came up as your x. So what am I doing over here? That সেটা হচ্ছে a equals to হচ্ছে minus cos t. So এই মাইনাসটা আমার অলরেডি প্রপোর্শনালিটির মধ্যে লাগবে। তার মানে আলটিমেটলি বাকি থাকলে শুধু cos t না। I'm gonna have minus omega square a constant. All of those constants are gonna be in front. That's why I'm not writing equals to. I'm giving arrows just to make sense with the for the numerical function, for the trigonometric function that is gonna dictate my equation. That's why I'm writing over here. So if a is given by minus cos t, is an expression of minus cos t. X should be expressed by what? Positive cos t. ঠিক কিনা? বুঝা যাচ্ছে কি বলতেছি?
Yes, sir.
So your correct response for this question should be which one?
সি।
C is your correct response. Did you get my point? It's very important that you do not mess up to observe this variable. Just don't look at the equation and jump into conclusion. Very important to look at the variable. যে তোমাকে যে গ্রাফটা দেওয়া আছে, the graph that you're provided with, what is the y-axis variable of that graph? Because you need to start your judgment from that point onwards slowly. Any questions so far? Everyone, বুঝা গেছে এটা সবার? উজমা, ইফাত?
Yes, sir.
আচ্ছা। Come to think of it, for the next set of equation, okay, then we have this equation. This is a pretty interesting equation. This is pretty important for us as well. If I just write the summary of all of this hunky punky that we just did up till now, I'm gonna write this. For this starting condition, at t equals to 0, x equals to 0, the equations look like this. X equals to a sine omega t, v equals to omega a cos omega t, acceleration equals to minus omega square a sine omega t. For t equals to 0, comma, x equals to plus or minus a, which means if we choose to start from the terminal positions, then x equals to plus or minus a cos omega t, b equals to minus or plus omega a sin omega t. If you wonder what is this is just the revert of plus or minus. It means if this is supposed to be plus, this is going to become minus, because differentiation of cosine gives you a minus output, and then the acceleration is going to be once again plus or minus omega square a cos omega t. এই হচ্ছে অল টুগেদার আমাদের বেসিক এক্সপ্রেশন যেটা আমরা এতক্ষণ ধরে আলাপ করছি and how করলাম. The next thing is that in all of these expressions, x, a, or v, they were expressed in terms of the variable t. The next part is that we want to express the velocity in terms of x. It means all of these things enable us to draw graphs of some variable x or v or acceleration with respect to time. But now we want to get an equation where v should be expressed in terms of x, so that we could ultimately draw a graph of v versus x. এরকম একটা গ্রাফ যদি আমরা আঁকতে চাই, তাহলে আমাদের কিরকম ইকুয়েশন আসবে? সো সেই ইকুয়েশন আমরা একটু ডিরাইভ করার চেষ্টা করি। লেটস সে V is given by choosing the very basic one, this one, omega A cos omega t, omega A cos omega t. So what I'm going to do, I'm going to give plus or minus root over omega square A square sine square omega t. I have given a whole square around this whole thing and given a root over, and because I wanted to root over, I have to give plus or minus. If you wonder why am I doing this, because it is easy to convert sine squared theta into cos squared theta. It is not so easy to convert cos theta into sine theta, because in the next line I'm going to write plus or minus. I'm going to take the omega A out, root over of 1 minus. Should I take the omega square out? No, I shouldn't have to take the omega square out. My bad. Let the omega square A square be inside. Plus or minus omega square A square into 1 minus cos square. আমি এখানে ভুল করছি না? বলুন আমি ভুল করছিলাম, দেখছো?
জি স্যার, নোটিস করছি।
I just want to find out if it is possible for me to give it a bit of a rotation. Can I rotate this? No. Okay, have a look at this expression. Try to understand the steps, what I'm doing here. First, I did a whole square and gave root over, and that root over brought in a plus or minus over here. So cos theta became cos square theta. Then I wrote the cos square theta in terms of 1 minus sine square theta. And then I keep the omega square in front and I multiplied the A square inside. My aim is to ultimately make this whole thing into X, because I'm having A square sine square omega t. So I can write A sine omega t whole square over here. I took the omega out in this step. So omega square becomes single omega on outside the root over sine. And this whole thing was written as X over here. So ultimately we have V equals to plus or minus omega A square minus X square. This is a pretty interesting equation. And this equation is equally applicable for this set of initial condition as well. So if we started the equation to be with this equation, we would still end up with this expression as well. Simply this is going to be a minus cos, and you're going to have the whole thing working just the other way around. This graph, this equation tells us a pretty interesting thing. Have a look. This dictates that if your x is 0, whenever x is 0, your v is going to be v max. And how much would be going to be that v max? This is going to be plus or minus omega a. If x is 0, this is a square minus 0 square, which means omega a. And that's essentially what happens for a simple harmonic motion particle. At the equilibrium position, we always have the maximum velocity, which can be in either direction, which can be towards right, which can be towards left, but the magnitude is maximum. And instances where x equals to plus or minus a, try to understand, x equals to plus or minus a. Plus a means on the very right side, or a minus a means on the very left side, or plus a might mean on the very top position, or minus a mean at the very lowest position. It can happen that way. For x equals to plus or minus a, v can be plus or minus omega root over of a square minus a square gives you 0, which means at terminal positions, the velocity of the object is always 0. This is a very important equation for us. We're going to be using this equation for a lot of calculation, especially whenever we'll be handling the scenario for kinetic energy expression. This is going to come out to be very helpful, to be very, very helpful for us. এই ডেরিভেশনটা কি বুঝা গেছে সবার এবং এই ডিসকাশনটুকু বুঝা গেছে কিনা?
জি স্যার।
দেখো কার কোনো কোশ্চেন থাকলে বলো, আল হেল্প। আচ্ছা এটা গেল। এরপর আমাদের যে জিনিসটা লাগবে সেটা হচ্ছে এরপর কি এনার্জি ক্যালকুলেশন চলে আসছে? We have the vertical spring oscillation. আচ্ছা এনার্জি এক্সপ্রেশনটা পরে পড়াই। তোমাদেরকে সিম্পল পেন্ডুলামের একটা এক্সাম্পল দেখাই।
স্যার আপনি যে ইকুয়েশনগুলো দেখালেন এটা হচ্ছে ফার্স্ট যে সার্কেল হচ্ছিল ওইটার জন্য না?
কোনটা?
যে ইকুয়েশন যেগুলো ডিরাইভ করলেন এগুলো হচ্ছে যে সার্কেলের পেন্ডুলামটা ঘুরছিল ওইটার জন্য না?
না 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 না, সার্কেলে যে পেন্ডুলামটা ঘুরতেছিল, সার্কুলার যে মোশন সেটা তো হচ্ছে theta goes to omega t and all the circular motion. We have projected the circular motion onto a two-dimensional plane. All of these equations are for the shadow.
আচ্ছা ঠিক আছে।
All of these equations that we have derived so far, x, v, acceleration, graphs, and everything, these are all for what was happening for the position of the shadow on this screen, for the simple harmonic motion of the shadow, which was derived from the side view of the circular motion, but these are not for circular motion.
আচ্ছা বুঝতে পেরেছি।
Beautiful. Vertical spring কি তোমাদের লাগবে? To be honest, actually, so never mind. দেখতেছি আমি কি করা যায়। This is a very nice graph. They have shown the horizontal position for the vector diagram with a vertical time axis. Have a look. T equals to 0, t equals to t by 4, t equals to half t. So this is for different position of this thing, and the particle was actually moving like this. So if you plot a graph of displacement versus time, this is how the graph is supposed to look like. And they have also shown the vectors for a horizontal spring for with relevant lengths of the spring. Have a look. Do you see what this graph means? Okay, this is a nice graph. The reason I'm telling it a nice graph is that, let's say you have this whole situation. You're having this object moving back and forth. This is a plus A, this is a minus A. You took time-lapse shots for different time instances, and then you plotted them one after another. This is how those time-lapse shots are gonna look like. They started from here, so net force is here, and then this one, this shot, and this is the equilibrium, then this is over here, over here, over here. They actually could show all the arrow directions with relevant size. So maximum arrow size over here, maximum arrow size over here, working in the opposite direction of this whole thing. And the spring lengths are also reasonably shown, which is the nice part of this graph. Like it. আচ্ছা, আমি ভার্টিক্যাল স্প্রিং তোমাদেরকে এঁকে দেখাবো, সমস্যা নেই, এখানে সবগুলো লেখা আছে, এটা বুঝাইতে একটু ঝামেলা হবে। I'll take a little break, like 4 or 5 minutes. আমি আসতেছি এখনই। What happens for a vertically loaded spring? Vertically loaded spring has a slightly different mechanism compared to the horizontal spring. This is because the weight is involved. So try to understand. Let's say we have a spring over here. It's blue. This is the roof or the vertical support point. Let's say the natural length of the spring is this much. If we load an object which causes the spring to become extended this much, other than object, let's draw a particle. It's easier to do with a particle. Let's say this is a particle of mass m, and let's say this much extension is e. The mass of the particle is working downwards, mg, and the spring spool is ke, and this is the current equilibrium. Now we can have a scenario of oscillation where this object is going to be pulled by a distance that is smaller than e. Try to understand this part. So let's say for a third figure, we are now gonna pull the spring by a distance slightly less than e. Let's say the spring is gonna be pulled up to here, let's say up to this level. So this was the equilibrium. Here is x equals to 0. For the oscillation that x equals to 0, let's say we pull it up to this one. So this is our x equals to minus a, considering vertically upwards as positive. So for this position, the force on the particle is gonna be upward force, or this, in this case, the upward force is gonna be the total pull of the spring, which is gonna be equal to k into e plus a, because now the spring is pulled by an a distance further downwards, and the weight always works downwards. Mg is still here. So in this case, the resultant force, which is going to be responsible for this motion, the resultant force for this terminal position is going to be this e minus e plus a minus mg. I'm showing it for the magnitude, but if I want to show this for the vector quantity, this should have a negative sign over here because the force is working in the upward direction. Let me just show. Yeah, so if I show this as a vector sign, so the upward force is the positive one and the downward force is the negative one. So this is perfectly all right. I don't have to give me minus, and I was wrong. I was sorry. So when the displacement is negative, the force is working in the positive direction. And also when the particle is going to lift itself upwards for the highest position, let me show that with green. Draw the whole setup with blue once again, maybe. So let's say the particle is going to rise up to this much distance once again in the positive direction. So this is going to be my maximum displacement over here, which is somewhat smaller than e. So in this case, let's draw the spring for the highest position somewhere over here, and let's say the particle m is over here. Mg is working still downwards. I should have written red. Mg is still working downwards force, and in this case, because the total upward movement is less than the initial extension of the spring, even at this position, the spring is somewhat extended. Try to understand this part. The spring is somewhat extended. How much is the extension of the spring? This extension of the spring should be e minus a. Try to understand. This was the equilibrium position. This is where the particle was at equilibrium. At equilibrium, the total extension of the spring was e. The maximum upward movement that the particle could do because of the oscillation, this was the minus a position. This is the x equals to plus a position. So the particle could rise from the equilibrium up to this much. Even when the particle is at its maximum position, the spring is still somewhat extended. That's why the pull of the spring in this case would still work upwards, and that force is going to be k into e minus a, and the mg is going to be the larger force. But in this case, the mg is going to be such that mg is going to be bigger. So I actually misdrew the length of this arrow. This arrow is supposed to become smaller. So for this scenario, the resultant force is going to be k into E minus A. This is the pulling force of the spring minus mg. And in this case, the total value of this thing is going to be, mg is going to be bigger. So this force is going to work downwards. So this is going to be happening for the upper part. The point that I'm trying to make, that if it so happens that the amplitude of the oscillation is somewhat smaller than the initial extension, then you're going to have the spring extended for the whole oscillation process. The spring is never going to become compressed. The spring is never going to become compressed. Important information. The spring is never going to become compressed. But in other cases, it can happen if the pulled direction of this particle for the oscillation was bigger than the initial extension E, then the particle could rise also upwards by that same direction when it's going upwards. In that case, the spring is going to become compressed for this much part. So up till this part, the spring would be pulling the particle upwards, but for this much section, the spring is going to start pushing the particle down. So you can have a bit of different equation for that scenario. In that case, the spring is going to push it down for this much. Let's say this distance is, I'm going to write, let's say D. So when the particle is going to be in the topmost position, in this case, the spring force is going to work downwards. The weight is also going to work downwards. So for that scenario, the total amount of resultant force for this position is going to be working downwards, and the magnitude of this force is going to be K into A plus D. No, sorry, K into D, which is the actual compression of the spring, plus mg. So what I want you to see is these two parts, that here the force of the spring was still pulling because the spring was not compressed, but here if the oscillation, if the amplitude of the oscillation is bigger than the initial displacement, initial deformation, then the spring might undergo a phase of compression. In that case, the direction of the spring force is going to change. So these are two different variables that we might have to consider for a vertical spring, for how much is the amplitude of the oscillation with respect to the initial deformation. So these are the two different variables that we can have to, that we might have to handle. This set of equation buildup might actually look a bit complicated, but it's not, because whenever we'll be working with numbers in the worksheet, there will be some mathematical calculation regarding this scenario. This will become much too simpler because all of these things will be calculated by numbers, so it will be far too easier for you to understand. What I want you to remember from this discussion is that if the spring is maintaining a state of tension, or if the spring is always at some amount of extension, the spring is always going to be pulling upwards. That's it. More deformation means stronger upwards pull, less deformation means weaker upward pull. But if it so happens at any point of the oscillation motion, the spring actually becomes compressed, becomes smaller than the original length, then the spring is gonna start pushing downwards. That can happen. এই ইনফরমেশনটুকু বুঝছো কিনা? If spring is extended, it always pulls upwards. If spring is compressed for certain part of the motion, for that segment of the motion is going to be pushing downwards. এই স্টেটমেন্টটা বুঝছো কিনা? হ্যালো, তো আছে? হ্যাঁ, আছে তো, বললাম আছে।
জি স্যার।
আচ্ছা, সিম্পল পেন্ডুলামের জন্য কি হয়? সিম্পল পেন্ডুলামের সিনারিওটা একটু দেখাচ্ছি। সিম্পল পেন্ডুলামের সিনারিওটা grossly generalized. Let's say we have a simple pendulum over here with a bob attached at the center. Let's say I'm showing it to be a particle. The effective length of this thing is L. Let's say we're going to give this thing a bit of movement over here. So obviously this is going to be somewhat above than the L position. So let's say this is my equilibrium position, and we have moved it over here. Let's say this angle is theta, which is the nice one. And to be honest, this particle is going to actually maintain a circular arc because the length of the string is actually working as the radius. The weight of the spring the weight of the bob is going to work vertically downwards. This is going to be mg for all the individual cases, so we can consider this thing to be force. The way this whole mechanism works is that we for a small value of theta, I mean whenever this theta is less than or equals to 0 through 5 degree, I shouldn't write 0 through 5 degree because I'm using less than equals to, whenever this angle is less than 5 degree, for a significantly long string, this movement path or this trajectory of movement is assumed to be a straight line. So what we are doing here is that we are considering a very small arc of a really large circle to be approximated as a straight line. That's the generalization that we're doing. And whenever the particle is above the equilibrium position, it's going to have some gp for these positions, and the weight is going to try to pull it downwards. If this is mg and this is tension of the spring, then t, this will be also theta, t cos theta will be balancing that mg, and we're going to have towards this direction t sin theta, and that t sin theta is going to be basically our working force to maintain the circular maintain the simple harmonic motion. The further is going to get closer to the equilibrium, the theta is going to slowly become smaller and smaller and smaller. As a result, the force is also going to become smaller, and that's how the whole motion can work. This is not a perfect simple harmonic motion, but simple pendulum is often used as the most common introductory example for simple harmonic motion. The reason I prefer not to show this as the very beginning example, because of this large generalization, that in a simple pendulum example, we consider an circular arc to be straight line. So, but it can be also considered to be a simple harmonic motion for practical purposes, but not if you consider, if you want to judge it by very exact or accurate theoretical purpose. It's not actually a simple harmonic motion because the movement path is actually not linear. The acceleration is working this way, and you have to understand that the displacement is actually changing direction, because at different points you have different position vector with respect to the starting point in different angles, but the t sin theta is always going to work towards horizontally to the right, because this is drawn as a component. So a proportional to minus x can be considered to be working, but it is not actually working because the direction of these two things are not perfectly opposite to each other. বুঝাচ্ছি কি বলছি? মানে এখানে একটা ছোটখাটো অ্যাপ্রক্সিমেশন আছে। আচ্ছা, এরপরে আমাদের যেটা আছে সেটা হচ্ছে এনার্জি গ্রাফ। এনার্জি গ্রাফ আজকে পড়ানো শুরু করলে শেষ করা যাবে না। এটা কি আজকে দেখবা?
স্যার শেষ না করতে পারলে নাই করি, এখন প্রায় তো শেষ ক্লাস।
হ্যাঁ, এটা শেষ করতে আরো ধরো 10-15 মিনিট লাগবে মিনিমাম এই পুরো জিনিসটা বিল্ড আপ করতে।
স্যার 3টা তো বাজে গেছে।
আচ্ছা ঠিক আছে, সমস্যা নেই, আজকে এইটুক থাক। আমি একটু লেকচার আপলোড করে দিচ্ছি, তোমরা যারা আবার রিভিশন করতে চাও লেকচার দেখো। আর হচ্ছে তোমাদের ইন্ডিভিজুয়াল ওয়ার্কশিট গুলা আমি যারা যারা এখন কালেক্ট করতে পারেন তোমাদের বাসায় পাঠানোর ব্যবস্থা করব। আমি এগুলা মেইল হয়ে গেলে তো তোমরা অবশ্যই নিউজ পাবা, আর আমি ওদিক থেকে মেইল ডিসপ্যাচ করে দেওয়ার পর তোমাদের চ্যানেলে মেসেঞ্জার গ্রুপে চ্যানেলে জানাই দিব যে জানানো হয়েছে। আর আজকে ক্লাস করে নাই হচ্ছে সাদিয়া। সো কারোর সাথে যদি সাদিয়া যোগাযোগ হয়, সাদিয়াকে একটু আমাকে নক করতে বলে যে ওর ওয়ার্কশিট পাঠাইতে হবে কিনা, ও আমাকে একটু জানাইলে তাহলে সহজ হয়, নাহলে আমি নক করবো না। তোমরা পারলে একটু তোমরা নক করো যদি কারোর সাথে কমিউনিকেশন থাকে, দ্যাট উইল বি হেল্পফুল। থ্যাংক ইউ ভেরি মাচ। আসসালামু আলাইকুম।
ওয়ালাইকুম আসসালাম স্যার।
ওয়ালাইকুম আসসালাম।